Okay. Okay.
No problem.
Okay. So today I'm going to talk about our recent work on a computer algorithm that overcomes the resolution limits. As Alexandra have introduced, my lab have been done a lot of things, but the main theme is we want to do imaging in live cells, in live conditions. So before I introduce our recent work, I need to go back a little bit to talk about the ultra-sensitive high-sense structure illumination microscope we did 5 years ago. So you guys must, I will guess this is an imaging forum. So many of you guys knows the structured illumination microscope. So I will not talk about the basic theory, I just talk about how it did. So when you are doing a two-dimensional structural illumination microscopy, you acquire 9 images with this kind of 3-pattern angle, like this stripe pattern going up and down, and 120 degrees and 240 degrees. Okay, at each angle, you have 3 different phases. And after you capture 9 images, you do a Fourier transformation, so convert into the frequency domain, and then you separate the high frequency information and stitching them together in the frequency domain, and then you do an inverse Fourier VINA inverse filtering or inverse Fourier transformation. Then you got the super resolved image. So I described all this process just to show you that the image you really see are not through your eye or through your camera. It's after all this computation, you got the image you see. So in this sense, it's a computational methodology. And 5 years ago, we find out that there's actually a problem with this kind of methodology. Take an example here. This is our fluorescence beads. And if we increase the background noise from 0 to 400 as this enlarged here, 1, 2, 3, 4 beads become aberrated, you will see. So why? So we find out that it's quite simple. This is because you are doing an inverse Fourier transformation to the assembled data you got. You are assuming all the signal originated from your object, fluorescence object, but in reality, there's a background noise, dark current. They are also being inverse Fourier transformation, which are amplified because you are divided by a very small number. So, and the citrus agents that you have less photons and much higher, much lower signal noise ratio, and this noise will also be amplified, and this is intrinsic to the structured illumination microscopy. So intrinsically, they are prone to artifacts. So what we find out at that time is we can use a very simple technique. For example, just take an example of this image. So anybody do image processing know that on the left, this image is corrupted with all kinds of noise. We can just do a median filter, which is replace the value of a pixel by its neighboring 3 plus 3, the median of the 3 plus 3, and you got an accurate reconstruction of the lady's image. So why? That is actually because we know that the real signal is continuously on the XY plane. And if we look at the stock market, we also see that all-time fluctuation are not really the trends. If we just do a rolling average and this period of time is shifting along time axis, we got this yellow line, which is the K line, which indicates the trends of the market of this stock, right? So by doing this, we also assume that the market trend or the information are continuously on the T-axis. So indeed, Leibniz have already said in 3 centuries ago that nature never makes leaps. So we propose that there are very strong and general prior knowledge, which is the spatial temporal continuity of the object being studied, which can be used to constrain the reconstruction process. So we change the original Wiener inverse filtering into a deconvolution process, adding the continuity on X, Y, and T as the penalty to guide the reconstruction. So what we have achieved, we can see here, we can achieve that 10 times less photons, but with the same quality data as you show here. If we just have 0.5 milliseconds exposure, this acting filament become aberrated with noise. But after using our spatial temporal continuity penalty, you can see they are reconstructing pretty well. And the intensity variance along this acting filaments also reduced from here to the red one. So we have the same fidelity, but we reduce the photon budget by 10-folds. Because of that, then we can image really fast process. For example, we can image insulin granules labeled by VAM2 fluorine under the turf sim. And under the turf, you just see a brightening. But under the super-resolution microscope, you see the formation of enlarged pore, which echoes what people have been founded 3 decades ago by Fries EM. What's more, because we have 300 Hertz temporal resolution, we can resolve the whole process, and we can classify it into different steps. If you don't want to go to really fast, I will argue that it can also be used to image really long time. As the example shown here, these are cuvette cell labeled with LIFAC EGIP. Upper is 7 milliseconds exposure with Wiener reconstruction. Down is 0.3 milliseconds exposure, but with Heisen deconvolution. And you see at the beginning, the quality of the data are similar. However, as time goes by, you see the Wiener failed because of the low signal noise ratio. You see a lot of artifacts. On the other hand, because of this is a time lapse, all these images are captured at 1 Hertz. And we can see because of our ultra short exposure, now Heisen sim can record like 3,000 frames without much photo bleaching, as the red line shows here. So we can image really long. And also, very importantly, we showed that we can image photosensitive organelles such as mitochondria, despite its theoretically resolution is less than STAD or STORM. So this is a table we summarized at that time. We can see, although it does not have the highest resolution, 90 nanometers for linear 2D sim or turf sim, but its image speed can approach like 2 milliseconds. It's the fastest than any other methodology used in live cell. But people still keep asking us, can we go even higher resolution? I would say at that time, I would say, oh, this is not very likely. The reason is because of we think at that time, the number of photons the number of photon flux would be saturated, as the example shown here. When we increase the excitation intensity, you see more and more fluorophore go from the on fraction to the off fraction. Correspondingly, if you look at the right, you see as we increase the illumination, we did not linearly increase the fluorescence intensity. It actually saturated at about above like 20 kilowatt per square centimeters. So with the limited number of photons, how can we further increase the spatial resolution? So we think if only we can have a methodology that uses these photons more efficiently, can we further push the spatial resolution of live cell super resolution imaging? In fact, there have been another class, a different class from current classical super resolution. People in the mathematical field or in the communication field have been talking about mathematical bandwidth exploration for a long time, dating back to 1960s. And in 1970s, there's RL deconvolution, and in 2009, there's a comprehensive sensing paradigm. However, for physicists or optical microscopists, it is really hard for them to believe that it actually can work. Why? I think the reason is very simple. So when we talk about the resolution is actually because of when you have a sparse, a fluorescent sparse A here, it actually emits light 360 degrees. However, only a group of light, a limited amount of light will be collected by your object. That is limited by your NA, numeric aperture. So in the first place, your object did not capture every light or photons it emitted. So when it converges back, it cannot converge into a very small or infinitely small spots, right? So the spots it converged will proportional to your to the negative of your NA, which is the resolution equation, the famous resolution equation. So the resolution is because you have lots of photons. You didn't capture everything in the spatial domain. If we talk about in the frequency domain, then the imaging process become the Fourier transformation of your object, or high and low frequency information, multiplied by the OTF, optical transfer function. And because your optical transfer function outside of the supporting region are all zero, it's basically a low pass filter. So outside of the supporting field, there's zero information. So if we want to reverse back, if we want to calculate back the object, what the object looks like, we can just do a simple division. F equals G divided by H. H is the OTF. From this equation of V0 deconvolution, we see that it is impossible if we just use this equation to extend any resolution, because H outside of this port are zero. So you cannot divide it G by zero, right? However, in 1970s comes astrophysicist Richardson and Lucy independently proposed another idea. So instead of doing a directed inversion in the Fourier domain, they say we can make a guess. So we can make a guess of the object F looks like, and then we convolve with our point spread function, and then we compare the data with the image we really get, and then we keep the similar one or the same ones, and then we make the different ones, and make the different ones multiplied by the H, the point spread function, again for another round of iteration. So presumably, if we can do this kind of iteration a sufficient number of times, then our guess would be very much likely the real object. But from this procedure, we can also see that there's no divided by zero operation. So theoretically, it may improve resolution. Indeed, the people shown as shown here, a twin star very close, if you just do RL deconvolution, can be resolved, which is outside of the support of the MTF, that is the microscope, not the telescope, not a microscope. However, they also shown if there's some complicated structure like the sunfly, something like that, then you do the RL deconvolution that does not result in any improving resolution, but just increase of contrast. So that's why, if you look at the textbook, the Fourier optics, it actually says something like this. Rayleigh diffraction limits represents a practical frontier that cannot be overcome by applying bandwidth extrapolation method on image obtained from conventional imaging system. So that basically say it's a theory, but did not work in real world. So the first thing we want to resolve is whether deconvolution, iterative deconvolution will improve resolution. So we make a simulation, because in real sample, you don't know the ground truth. But in our mind, we almost know in our simulation, we can have this ground truth image containing all kinds of frequency information. And then we simulated being imaged by a microscope. That is means low pass filtered, all the high frequency information are turned to 0. And if you see this periodical grids now become flat plateau, wide plateau. However, there's one critical thing I need to mention here, because this is a simulation, it has no noise. We only trim off the high frequency information, and we can just throw into the MATLAB to do RL deconvolution for 20,000 times. You will see the high frequency information coming back. And you can see here, this periodical oscillative traces all coming back, although their amplitude are still not the same. If you do more, 2 order more for letting the computer run a week something, and now you can see almost exactly recover the high frequency information. So theoretically, even the high frequency information are trimmed for this sample, it can be recovered when you have no noise. However, in real world sample, you always have Poisson and Gaussian noise. And you will see when we have noise, then things change. If we just do RL deconvolution, without noise, you can resolve like 10 nanometers apart. But with the noise, now you can, the best you can get is like 100 nanometer or something more, depends on the noise. So the problem becomes, how can we improve resolution in real world microscope samples? So we come up with another idea. So when we talk about high sensitive, high resolution fluorescence microscope, we are actually the high contrast, high sensitivity coming from the facts. We are selectively highlight only part of the image. Okay, so what does that mean? For example, if we take a look at the nuclear pore complex, it is formed by like 20 or 40 proteins. It's a big protein complex. But if we just label, for example, NUP 98, there are actually only 32 copies, like this red dot shown here. And the wide field is a large blur, and the area scan smaller blur, and instead a ring merged. And under the storm, now you can see spots like the ring structure. So we can immediately realize that when we have high resolution, the point spread function should be, the theoretical point spread function should be smaller, and your sample will be smaller, or your signal, fluorescent signal, will become less dense or sparser on your image. So that actually means sparsity is another general feature of fluorescence microscope that can be used along with spatial and temporal continuity. So having that in mind, then we say that when we got our image, we can use the sparsity and the continuity as the general prior knowledge to constrain an iterative reconstruction. And then we do RL deconvolution. So the equation compared to 5 years ago, now, besides the Heisenberg penalty for the spatial temporal continuity, we have a L1 penalty for the relative sparsity of your image. Okay. So after this, we do RL deconvolution because we want to first have the image push the image more and more like the ideal image without much noise, and then do the RL deconvolution. And with the new methodology, now we can show that for the simulated results for the paired line, previously, for example, here, for RL deconvolution, we can only resolve up to 100 nanometer already with a lot of artifacts. But with the sparse deconvolution, we can resolve like 60 nanometers, okay? But people may say, okay, this is your simulation. You can do whatever on your simulation. We have to benchmark it with the ground truth, which is obtained by another microscope in live sample, in real world sample. So we make DNA origamis, and with the pair of dyes labeled with a distance like 60, 80, 100, and 120 nanometer apart. And we mix them together, put it on the glass cover slip, and split it into two. Half of them will go to our turf sim for imaging and use sparse deconvolution, and the other half to go to the point-based supraillusion methodology called the ROSE, developed by Ji Wei and Tao Xu in Chinese Academy of Science. And then we can see that both this method get the same distance, and also the distribution on the proportion of different distribution on the cover slip also the similar, indicating that we can actually get accurate numbers, separations of these paired dyes. So how about the line structure? So we can use commercial Argo slides, which have this kind of structure, a pair of the lines 60, 80, 120 nanometer apart. So if we just do thin raw data, you cannot see. But if we just, after that, we do RL deconvolution, you won't see 90, separate 90 or 60 paired line apart. If you do more RL deconvolution, like 50 times, you see a thinner line, but twisted. This is artifacts. However, if we use sparse deconvolution, we can actually resolve two lines 60 nanometer apart. Here, I also want to emphasize this improve in resolution also depends on your signal noise ratio. If the signal noise ratio deteriorating, you will see that, for example, at the 1/8 of original signal noise ratio, now we cannot resolve 60 nanometer apart. We can only resolve like 90 nanometer apart, okay? So this is determined by the signal noise ratio as well. How about the complicated structures? So we can use expansion microscopy, the sample like microtubule or ER be expansioned and imaged either with structural elimination as ground truth, or just use the sparse deconvolution on the wide field. And we can see that they correlate very nicely, even for these complicated structures. So having established that our method actually works, now we can test previous state-of-art samples people have shown. For example, caveolin structures previously only, and the nonlinear sim, you can resolve these structures because they are less than 60 nanometers, less than 70 nanometers. However, now we only use 9 images with linear theme, and after manually upsampling and do sparse deconvolution, we can resolve these ring-like structures. Okay. You may wonder, also sparse deconvolution can also remove background, because when you have background excitation or emission from out of your focal light, you also create your image not so sparse or more dense. So it not only improve resolution, it also improve contrast on this sense. And also we benchmark on the nuclear pore like structure, because it's inside the cells and on the nuclear membrane. And we shown here that we can resolve this ring-like structure of the NUP98 labeled structure, and we can image them for like an hour to see how their shape fluctuating on the nuclear membrane. And we also can do quantitative measurement of their diameter size after calibrate for the pixel size. We can get different nuclear pore like the structures, their diameters, and this diameters echoes very nicely with what people previously have shown with the fixed supraillusion methodology, but done on fixed cells. And the benefit of our method it's a algorithm. So that means we can use our old data, like data 5 years ago, and see what else can we see. Actually, we re-examined the VAM2 fluorine, the fusion data of insulin granules. And we now, because our resolution improved, now we can see much smaller fusion pore, as smaller as like 60 nanometers, but on average, their size is about 90 nanometers, and they last only for, on average, 10 milliseconds. Okay, that's a new, we think this is a very important new fusion intermediate states, with only achievable by this spatial temporal resolution combination. And we can also do it easily on the 2D theme, because each color can do sparse deconvolution individually. Here we show an example of both mitochondrial out membrane and the mitochondrial matrix. And for this matrix protein, you can also see a kind of like the crystal-like structure. And you can see this with only TOM20 structures, which probably like to be mitochondrial-derived vesicle MDVs, very dynamic. And also we can see, for example, how this green LAMP1 like the structure, how they contact with the red mitochondrial structure like here. And then in the end, if you see, look closely, in the end, it will take a piece of the TOM20 within the lysosome and go away, okay? And in the end, you see within the luminance of the lysosome, you see this red like the TOM20, okay? And also we can see how mitochondrial contacts with the ER-like structure. So a short summary here is, now with the purely computational algorithm, deterministic, we can now further improve our resolution from 90 nanometer to about 60 nanometer, better or even better than 60 nanometers, depending on the signal noise ratio, okay? But can this method be applied to other fluorescence microscope? We think probably yes, because the spatial temporal continuity and the sparsity should be general prior knowledge for all kinds of fluorescence microscope, but not just for them. So we try another one is the image scan microscopy or confocal like the structure illumination supraillusion microscope first proposed by Shepard and also lately reinvented by Adlan and Andrew York. So we use a commercial live SR system, and we labeled this COD7 cell mitochondrial with TOM20, and different color indicate a different ZX layer. On the left is the raw data, is a dividing COD7, so it's a little bit thicker, 7 microns. And on the right, you see how it being after being sparsely convolved, you see crystal like the mitochondrial out-membrane structures. And we can also make a comparison with previously what other people have shown, like use 3D storm or photoactivable nonlinear scene the lattice light sheet. I would say with a commercial system and adding with our super-elution deconvolution algorithm, the effects is amazing. And here we also show another case. Previously, all the case we are breaking the limits of your fluorescence microscopy. We also know that another factor that may limit your resolution is insufficient nyquist sampling. For example, if you are using EMCC camera to on your spin disk confocal system, because the pixel size of your EMCC camera is larger, the pixel size is larger, so often you are not achieve your maximum resolution because of insufficient nyquist sampling, as the example shown here. For that kind of sample, we can actually do a sparse deconvolution. If we just do on sparse deconvolution, you'll see FRC quantified resolution not increase much. That is because it's limited by your nyquist sampling criteria. However, we can do artificially sampling of the image, and then we do sparse deconvolution, and we can see. You can indeed see a large increase of the resolution from 180 now to like 100 nanometer. And we also benchmark our method on other technologies like STAD, like a point scanning confocal, now become a sparse confocal resolution improved, or STAD, or do sparse STAD, also resolution improved. And we also try on our invention, miniaturized 2 photon in live animal. These are Psi1 labeled, sparse labeled neurons and dendritic structures. And here we'll see on the left is raw data, in the middle is the RL deconvolution, color indicated different layer, and on the very right, sparse deconvolution. Indeed, we see much more intricate spine structures. And if we plot the OTF, you can indeed see an increase of OTF. That's also another evidence of the improve of the resolution. And the last, I will emphasize that the whole pipeline are required. These are simulated data as shown here. So if we just have the sparsity and continuity without deconvolution, it will not work. It will not go to this ground truth or like this one. If you just have continuity plus deconvolution, you got a smooth image, but not much improved in resolution. If we just have sparsity and deconvolution without the continuity to constrain the noise, you see aberrated image, okay? And also we compared our method with other type of comprehensive sensing, like the optimization procedure called FISTA or NLHT. You will see their quality much more like the sparsity and the deconvolution. Your image becomes sharper, but with a lot of artifacts. And we also test, for example, if just use pure denoise or TV deconvolution, or just do RL deconvolution for multiple times, it doesn't work. So you actually need the whole pipeline. You need the spatial temporal continuity as a and also the sparsity, all two together to reconstruct to constrain the process and followed by the iterative deconvolution. And in our paper, we also test a large array of data sets. We show with sufficient signal-noise ratio, their resolution can be improved. So summary here, what I like to state is we have developed the first general computational super-resolution method that reliably extends spatial resolution beyond physical limit posed by the hardware or posed by your photons flux numbers. And if we combine it with our 2D structural illumination microscope, it can enable 60 nanometer resolution at 564 Hertz frame rate. And it can also be combined to the spin disk sim, which is easy to use and enable full color 3-dimensional 90 nanometer lateral and 250 nanometer axial resolution in live cells. And it can also be applied to other methodology, including light sheet, the data I didn't show here. And if you are interested in the process, we also write notes in the Nature Biomedical Engineering portfolio for other people to see. So finally, I would say that sparsity, continuity are very simple ideas. But when we combine together to devise our deconvolution process, it becomes really powerful. So I would like to say that echoes what people have always thought, that it is always the simple that produce the marvelous results, or in Chinese, 大道至简. Okay. Finally, I would thank the people who actually do the work. So this work is a collaboration with the Professor Haoyu Li in Harbin University of Science and Technology. And the people who did the work, the first authors are Wei Songzhao, Shiqun Zhao, and Liu Juli. And thank you, and I will stop here. Thank you.
Thank you very much. What a fantastic talk. I mean, how wonderful to see all these kind of techniques coming together and delivering such kind of fantastic results. I mean, that's really was very special. We also learned a little bit Chinese, which I also liked a lot.
Yes, the last
thank
one.
You very much.
Yes, thank you. Yes.
As the tradition is, we normally, I think if people could join the quiz, I put the quiz into the kind of chat actually, so you can actually, I think that's, I can do it again if you want, or we give the speaker a short break. And so if you have questions, please also put them into the chat. So here's the Mentimeter, and I will share my screen in presenting mode, and some people have already picked up. So I have a very biased first question, so there will be no points for that one, but okay. I'm asking, I think I go here, so this one here. I'm asking you what influences the quality of your images most. And I think what I expect a few people to say the Queen's Jubilee, but maybe not so many, because that's happening very soon, and there's a lot of things happening around it. So this is a bit of a cheeky question, obviously. Yes. So I'm just waiting for a few more people to join, and if you can, we can have a few more people. Maybe this is maybe this is kind of, so the development of new software, as you can see, is actually the winning influence. And which people will see that that will kind of influence the quality of your images. And I think that's very much from your talk as well. I think that was, so I should go forward as well now here. Let me just go to the next. Yeah, so have a few people joining. Come on, join a few more people. It's always people. Yeah, go on. Yeah, okay. Okay. Oh, I'm always. Oh no, wait. So okay, I always do this a bit wrong because let me go back here. This is typical. Okay. So let me just go. Okay, so this is question 1 of 5. Am I doing it wrong? So you have entered. Can you enter again? Okay, that was question 1. I hope I got it right. I haven't done Mentimeter for a while, so okay, so this is kind of a oh no.
No result yet. This
oh no, I'm doing a funny thing here. Oh, there's a difference. Okay. Okay, answer first to get more points. Ah, okay.
Okay.
So this is your first question. I'm sorry.
Yes.
Fundamentally, microscopy is limited by the diffraction limit because insufficient Nyquist sampling, aberrations in the optical system, or the numerical aperture of the objective. And that time is up. And we have 4 people who picked up that it's the numerical aperture of the objectives, but obviously other contributing factors. But let's see the leaderboard on this, which I haven't used actually that much leaderboard on this. Okay. Okay. Sorry, I'm kind of, okay, yeah, there's leaderboard. So we have some funky names: Brun, the Brocken, Heartstorm, Pick, Jan. At the moment, Jan is the fastest. So let's see how it continues. So we get question 2. Okay, and it says answer first. So theoretically, can deconvolution algorithms be used to improve the image resolution? And there's the possibility to say yes, no, and sometimes yes, and sometimes no, which is maybe the safest way out there. I like that one. It's lovely. Okay, I think people like this kind of slightly undecisiveness here in this kind of question and answer options. And Jan is still doing very good here, so he still continued to be the first in the leaderboard. And let me just go to the next one, question 3. Okay, and again, if you fast answer, you're better. So iterative deconvolution of fluorescent images obtained by a microscope 1,000 times will lead to. And the options are improvement of resolution, artifacts are sharpened, and better contrasted images. See in 2 seconds what the answer is by most of them. Again, we have like, oh, we have quite a lot of people getting that one slightly wrong, but
yes.
Let's see who's now in charge. Yeah, that was a tricky one. I was also thinking when I put it in, I had to think. And we don't give people much time. So Jan, you've been taken over by someone who got that one right. And question 4, but 2 more questions to kind of obviously catch up on this. And again, as faster as better. In live cell super resolution imaging, the most critical parameter will be the spatial resolution, the temporal resolution, or the matching between the 2. And you saw some, I mean, there were some fantastic images actually in a super resolution live cell imaging. You've done amazing in the presentation. I think we were very spoiled because that's extremely difficult. Okay, and again, most people got the answer right. And Jan is kind of moving forward again. Yeah, not to be kind of brilliant, really nice. Okay, one more. And the last question, now take good kind of care, you get it right as well. which one does not distinguish between super resolution enabled by the sparse deconvolution and the deep learning based methods. And then you have the need for non-biased quantitative assessment, deterministic calculations versus probabilistic inferences, and the use of general a priori knowledge versus dependence on the specific. Oh, that was a difficult one. Even reading it was actually tough.
Yes, that's too long. Sorry for that.
So, I mean, again, be careful with the answers, but I think this was really a good learning as well, because it's a very nice way of kind of looking back at your lecture. And we have Jan, who's been very good all the way through. Yeah. So Jan, yes, if you want to win the Foldscope this week, then please make yourself known to Georgina or one of us, and so we can actually send it to you, because we feel like that's still kind of a nice obligation and duty to kind of provide people with microscopes, even if they're just folded little paper microscopes. So that comes from the tradition of this kind of lecture series. So, and also, yes, I mean, anyone who would like to, you know, if you want to suggest a speaker, if you have other colleagues who you think would give a good talk, would kind of just share, even PhD student, postdocs, anyone would like to kind of share some of their ideas and present here, please let them know, and just let them contact us, and we'll be super happy. I saw there was a question, yes, something about ImageJ. Where is it now?
Yeah, so
I missed it actually. Oh yeah, with the Fuji plugin. So you picked it up already.
Yeah, the Fiji one, actually, the Fiji one, we don't have the Fiji plugin, but in the GitHub we have a MATLAB version as a standalone software. A brief demo, okay. I don't have the MATLAB version on my computer, but let me see whether I can find the supplementary of our paper just to show everybody. Let me see.
Yeah, that would be nice, so we can share.
Yeah. Yes,
but it is open access.
It's open source.
Open source.
Yeah, it's all open source, and you can also check in the code to make sure we didn't cheat. Actually, didn't just clipping something off. But the software, let me just show briefly here. It should look something look like this. Okay. So you will choose your pixel size, wavelength, your numeric aperture. This actually doesn't really matter. You can choose a little bigger one, because we find out if you choose this NA, large NA will converge faster. Small NA will also converge, but you take longer times. And because we have a two-step process. The first one is this sparse iteration times, and with the continuity and with the fidelity, and this axial continuity, which is temporal one, we dissociate with the spatial continuity, which is the inverse of the fidelity here. Because sometimes if you just take time-lapse image, that means two images take at a relatively longer interval, we want to reduce this number, okay? Because they may not continuous, because you are taking too long to take two images. But if you take really fast images, then you can increase this one to antagonize the noise and the artifacts and the sparsity. And also this one, deconvolution time, means the RL deconvolution time. RL deconvolution is already accelerated version, so do 10 times is much more. You may say 10 times for this RL deconvolution, which is used in the MATLAB, equals the RL deconvolution you use in the ImageJ one, deconvolution lab one, like 1 to 100 ratio, something like that. So it's largely accelerated. And here you can also choose subtract your background or not. Usually you can just go without background, no subtraction. And here you can choose RL or Landweber, which is similar, but may work better one another on different sample. And here we also provide a choice for oversampling. So if your image is not meeting the Nyquist, and then you can choose oversampling, manual oversampling. But it also comes with the cost of the artifacts, and you can do 3D. Then here become Axel. If it's 2D, then here is T. Okay, and you can also use GPU acceleration. And also, I want to emphasize, because of the parameters associated, we have a very detailed step here in the supplementary figure 14, and also associated supplementary on how to choose these parameters. Okay, for people interested, please refer to our supplementary material. Okay, but it's all yeah.
Do you also provide like the data set so people can also work with those? I mean, that everything will be available, so they your own data set, so that they can compare it running and then their own data. It'd be really nice to keep all of this somehow available, so people can kind of keep communicating about it. I'm sure it's happening, but I mean, I just find that's actually the most important thing at the moment for these kind of software algorithms. Kitty wants to comment. I'm sure I see his hand raised, and he probably has questions and comments.
First of all, like many happy returns of the day, Liangyi. I hope you had a good birthday and you had good celebrations going home. Can you hear me or not?
Yes, I can hear you.
We can hear you.
Since you were on the supplementary material, I'm wondering if you have some analytical solution that describes the relationship between fidelity, sparsity, continuity. Have you derived that one somewhere? If you were scrolling in the supplementary material, if I can see the equation somewhere, I'm sure. Like or some analytical solution.
No, that's not an equation. That's something we find it useful, like a 110 something. I mean. You means this one?
We have, let's say, like you said, it's inversely proportional, which I imagine, but do you have some solution like mathematical formulation or something?
No, we don't. No, it all depends. It actually depends a lot on the signal noise ratio. If your signal noise ratio is poor, then you cannot do improve resolution, but just increase contrast. But the fidelity versus sparsity, approximately 20 versus 1, is just pure experience by tuning these parameters, fine tuning. But this serve as a good starting point. But then you have to putting this up and putting that down to see all this kind of data. Yeah.
Do you think if someone has integrated this in the classical, resolution precision formulas?
For sorry? Yeah.
These factors coupled in.
This is the very difficult part. I would say explain in two parts. First, just answer your question. Also, comments to all my quiz when I say, do you think our deconvolution can improve resolution or not? I say sometimes yes, sometimes not. And sometimes yes. Why? It's because it depends on the sparsity, the relative sparsity of your sample. It works mostly for fluorescence microscope because they are relatively sparse, but it won't work for like EM data. I don't think so because they are not sparse. But in our paper published, we didn't have a mathematical proof yet, but we are close to it. We are doing that now, but that only give you a boundary, just like computer sensing give you a boundary on theoretical cases, upper boundary. Okay, so that's one thing associated with your problem.
But then you can couple that upper boundary, let's say like for a continuous structure like microtubule, if you, let's say, deconvolve and your tubules gets thinner, but then you start breaking them up. Instead of continuous structure, you start to see, you know, dots on a line like structures, which is very common in high resolution method. So in that case, like you can couple in this continuity factor in, right?
Yes.
To compromise for the sparsity due to, you know, let's say manipulated precision. Yeah.
Yes, for the second part, I agree. We don't have equation now, but what now we do is we choose the sparsity parameter and the iteration times, because these two are pushing the resolution. Okay, and sometimes if you push too much, you got artifacts. So how do we decide whether we have a real resolution but not artifacts? Or we also judge by one criteria whether the resolution is allowed by your Nyquist sampling. Okay, for example, if your pixel is only 32 nanometers, if you see a structure like 40 or 50, you know that you are pushing too far. Okay, so that's a general rule of thumb we are now using. Okay, but I suspect in the future we probably have better ways or even deep learning ways to know that you know how to when to stop, something like that. Yeah.
Thanks a lot.
Yeah, really nice. Thank you. Someone is asking, Anne Wheeler is actually asking if it will be possible to maintain the code going forward, because that's often what happens with software projects. Will they cannot be maintained when maybe the postdoc or PhD student is leaving? So
I see. I think we have students and the PhD student, the first author, I think he is keeping maintaining and maintaining the open source code. We also have a startup company to sell the packaged C like the codes, which are commercially also available for people who just wanted the results faster.
Oh yeah, excellent.
Yeah, that's also an option. Yeah.
So people can put their data into an online cloud-based.
Yes, that's what we think, that with the online cloud-based, that then you can try a little bit, then you got the software and you can run on your own data.
You can put your company here as well, if you like, into the chat, if you have the link. We can,
okay. That's a good idea. Yeah, I should put it in.
Nice,
currently, it only has Chinese website. I say they should have an English website.
We'll get Google Translator or one of our postdocs to have a look at it.
Yeah.
Is it Mandarin or Cantonese?
Oh, okay. That's good.
Mandarin, so if it's Mandarin, we'll probably be okay.
It's a Mandarin, and it's come with the hardware and also the software. Yeah. But
yeah, we have lots of Chinese postdocs now also in Cambridge, so I think it shouldn't be a problem.
Okay, that shouldn't be a problem. Yes, agreed.
Thank you very much.
Thanks very much.
I think this is the last few minutes, so we are running now out of time. But thank you very much. It was a real pleasure and really fantastic. I hope you see the Northern Lights later this year, so behind you, and you can celebrate your birthday now.
Thank you.
Maybe
it's a great experience.
It was really lovely. Thank you.
Yeah.
And people can contact you if they have more questions. So we share always the contacts, and your talk will also be on our YouTube channel. So really lovely. Thank you very much.
Thank you.
Thanks everybody for joining.